All right, got to hit my marks over here. All right, this particular presentation is about GPS, or as it is more generically known, GNSS. I'm Mike Toecker. I'm coming up here basically as an independent researcher. You've seen me on stage doing some work with DARPA. That's some other work that I do. That's a little bit less technical than what I've been trying to do here. So what we've got right now is that GPS or GNSS in general, pretty ubiquitous in industrial control systems. All right, you go and you do an assessment of most substations, most generation centers, a good chunk of oil and gas, water systems. You're going to find a GPS clock somewhere in there, all right, because everybody wants good time. They want to know what time it is. They want to be able to sync up logs, things like this. It was actually a major component in the recommendations after the 2003 blackout. All right, literally came through and said, we have no idea. We have logs from here, we have logs from here, we have logs from here. There's some logs over there. We have no idea how to put them all together and set them up in a single time frame. And it actually found its way into it, which is one of the reasons why we find GPS clocks all over the place right now in ICS. So I picked a couple of big examples here on my left. That actually came out of some diagrams from a publicly available design diagram for a generation station that is actually an NTP clock. Parts of this is GPS clocks and what they communicate to in substations. That's the second one from the left. And then here's some actual RFPs that say, look, hi, we would like GPS, please. We really need it. We want to make sure our SCADA master always has it. So accurate time for everything. And once it's on your network, it can communicate with anything on that network. A little bit of GNSS spoofing to date. All right, we've been doing this for years. All right, this is just public sector. I'm sure there's all sorts of other crazy stuff that happened before this. All right, we're talking about sending yachts off of, out on their own. We're talking about redirecting cars so that they find their way, to places where you didn't really want them to be. We're talking about teleporting people so that they can play Pokemon Go from anywhere. So, there are all kinds of uses for GPS spoofing, all right, and being able to change time, all right, especially for PMUs, which are used in the electric sector for tracking data associated with the electric power grid at a real fine degree of detail. And they're all synchronized via GPS clock, all right. This presentation is not this presentation. This ain't about spoofing, because I think we missed a real big problem here, is that spoofing can happen because the signal itself cannot be verified, cannot be validated that it actually originated from something that the United States or Russia or China or Europe owns in space. We have no idea. And so you can just point an antenna at something with the right stuff, give it a GPS signal, and everybody goes, oh, it's GPS. I'll totally listen to this. Okay, I'm at the North Pole. How did I get here? So that presentation is not my presentation. My presentation is actually looking at the core problem. This is unauthenticated radio from space, all right, that we allow into industrial control systems just because we feel like it, just because we need it, just because we think it's a really good idea. So I'm not actually talking about spoofing here. I'm talking about building a command and control channel using GPS. So the idea is that you use the same stuff that we have in the public in order to build up a control channel so that you can actually work on something like through some supply chain security hack or malicious firmware, or maybe the device itself got owned in a previous attempt and you didn't catch that it was there. But the idea is that it provides signaling for something that's already resident on the network. Because you don't need, like we figured this out with diodes, you don't need bidirectional communication in order to get data from point A to point B. You don't. You just need to be able to have one way, and one way is good enough. So this is kind of amateur hour here. This is not my normal strength. I kind of picked this project because I figured it would be a nice multi-year project. I get to work out some strengths. Actually, I'd work out some weaknesses that hopefully would turn into strengths, which I would really like. I get to work on radio-type systems before, which I haven't had a huge amount of time to do since college. I get to build some of my code capability and make us a point about supply chain security. But, I'm usually the one who is, up on stage talking about fuzzier things sometimes. So expect to see me again in the years to come regarding this, but this is definitely a little bit of amateur hour. So this is not just about me building something awesome and making a proof of concept. because it's not about that. I didn't get there. So I'm going to tell you a lot about my failures as well as my successes here. So I don't want to say I'm bearing my soul, because I'm not. I think this was a really fun project, and I really want to share it with a bunch of people, because waiting 2 or 3 years in order to do this seems kind of painful. It would take a while. So the original high-risk plan was, all right, we start at the hardware level. I go out and I buy a GPS clock. You can get these on eBay. This is a decommissioned one. Probably came out of something interesting, or maybe not. This particular one has been, it is no longer top of the line. You can't buy these anymore. The vendors discontinued them. So I'm not too concerned about issues related to that. Plus, older stuff is easier to work with. All right, so that was the original one. But of course, if you're going to be doing that and you want the GPS clock to communicate with things, you got to put on a network switch, and you got to be able to communicate with it, and you have to be able to have cables. And I didn't put my entire rack of automation stuff in here, but I've got another rack behind this that has a bunch of automation stuff that I was going to throw on the network too. So once you have all of that, well, you need a GPS antenna. I mean, you have to be able to accept a GPS signal from something, so there's a GPS antenna. And then, of course, you have to be able to generate a signal. This is getting a little bit complicated. Seems a little high risk. So the HackRF is what I was planning on using as far as generating a GPS signal goes. Nice open source library. I'll get into that in a sec. Once you have that, then you need all the accoutrements that are associated with it. You'd be surprised how many antennas you can buy that do GPS, all right, and how many of them actually receive GPS. And down in the little corner on the left-hand side, that is actually a special NESDR that has a special set of circuits inside that allows it to do active capture for GPS antennas, so I could validate that the signal that was coming out of the HackRF was actually working. All right, so this is getting pretty complicated. If you've ever done any work with HackRF, it doesn't like VMs very much, so I've got a dedicated computer now to be able to use for this. So this is starting to look more Pelican case than anything else. And for somebody who travels as much as I do, I think I had maybe 1 week, November and December on my own, for instance. So, and then of course, power, you have to be able to tear it apart, you have to be able to interface with the data, you have to be able to pull the card, you have to be able to... So anyway, this turned into a very high-risk operation. Way too many variables to control. At any point in this line, even if I developed really good code, any single one of these components could fail. I might not know which one had failed. I might not know exactly how to figure out whether it had failed. I'd have to build testing tools for each one of these components to make sure that each one worked in sequence. So, high-risk plan. The other one, too, is when you buy GPS clocks and you go and hack them, you might end up on a list somewhere. So I turned this into an achievable plan. What was the core argument I was trying to get across? All right, what was the big piece of this? And the big piece of this was the signal would have encoded commands that would then be interpreted by a receiver that would then run a specific set of hacking tools on a system. And so working with this, I went through, did a lot of Googling, did a lot of viewing of presentations on YouTube, made a few calls, and came up with a nice, simple series of software, and purely software. No radio in this whatsoever. I don't need a radio in order to demonstrate a POC. And then I can expand it. I can eliminate that big red box in the center and put a radio in whenever I feel I'm ready. So the idea is that I modify a project called GPSSDR Sim. If you know what this is the high-profile spoofing code that's been put out on the internet. Freely available, it's a single C file. And what it does is it actually generates baseband GPS, right? Simple. Shoves it into a file. That file you can generally load into a HackRF, all right, and you can go play Pokemon Go anywhere. So this file, at this point, once it's built, all right, and once I've modified the GPSSDR Sim code in order to put the commands inside that I want to mess with, this would then get loaded into another piece of open available software, and this is actually open source software. This is GNSS-SDR. I'll go into these a little bit more, but this will actually accept this file, process it like it would radio, and then it actually spits out GPS information. So it decodes the radio information itself. And the intent is that I modify this open source library in a similar manner that I would a GPS clock and allow it to run those commands that I'm currently working on. So this fits, and once again, run commands on the local system. This I can take with me on Christmas, and I can do basically development anywhere. I can open it up on a plane, and so long as there are no nosy neighbors, I can work on this without any issues, and it's very much simpler. All right, I've removed a lot of the risk from these components that I don't have control over, and a radio environment that I don't have control over, as well as the potential that there are components that I can't get access to. So we've turned what is originally the high-risk plan into something a little bit more manageable. So for those of you who are looking to do really complex operations like this, do your best to figure out where your risk points are, all right, where you have capability to figure something out, because my original one, I didn't do that. So this new one, that's what I'm working on now. So again, this was the almost achievable plan. I think if I'd had 3 more weeks, I would have been fine. I didn't quite make it. And the other one too, it's also nice to not be on a list, because none of this is in any critical infrastructure at this time. All right, so it lets me go through without having to worry about somebody saying, hey, this guy's working on GPS, he's hacking it. So a little bit of fast facts. GPSSDR. This was a neat piece of software. It was supported by Google's Summer of Code program. It's available on GitHub whenever you want to pull it down. It is under active development. I believe Google Summer of Code is going to be sponsoring it again this year. Full development list. And what it is it's a fully object-oriented built-in C, C++ that takes in either RF or the raw signal file and then processes it all according to a series of rules. But all of these rules are loaded via configuration file. So you can actually build a configuration file that takes your flow graph all the way through out to your eventual output. It's a really, really clever piece of software. I almost felt bad adding really nasty commands to it. Yes. Next one up is the actual GPSSDR Sim. This is a pretty bare bones piece of code when you look at it in comparison to GNSS-SDR. This is basically a single file of C. And this single file generates the bare minimum necessary in order to spoof location and time. And it requires additional information that you have to load from, I believe it's NOAA, but I might be wrong on that side. Basically, it's all the GPS data that is generally updated within the GPS constellation of satellites about once every 12 hours. And it tells the GPS satellites, hey, we're going to be in this position at this time, so you can be prepared for us at that time. So these are the 2 large pieces of code that I am working on and will continue to be working on probably for the next year. So some GPS level 1 protocol in a nutshell. It's on 1547. You can't just pull this radio frequency out of the ether. It's one of the weakest signals that you'll ever see. It requires a specific type of antenna in order to pull it off. The HackRF will do it, as will the NESDR that I was using as well. And the intention here is that you come in it's basically a very large data frame. And within that data frame, you have 5 subframes. The first 3 are the ones that GPSSDR Sim, the spoofing program, uses and generates on its own. And it generates on the fly based on if you want to send it to the North Pole or if you want to have it run or lap around the White House or something like that. So those 3 frames, I don't care about. Not for my project. They're neat, don't get me wrong. Really great research, not something that I'm looking at. The fun parts for me are the subframes 4 and 5. These are composed of 25 different pages. So a big constellation of satellites, 20 plus GPS satellites, each one of them will have a different subframe 1 through 3. But for 4 and 5, they actually transmit the same data over and over and over again. And it's the exact same data for each satellite. The entire network sends out all of that. And the way that that works, because they don't exactly, there's nothing like collision detection for radio, is that they use CDMA in order to allow simultaneous just burst transmissions of this. And CDMA itself, each satellite has its own code, and you can extract the individual satellites themselves directly out of the radio by just normal CDMA stuff. All of this, by the way, I didn't have to build. All of this was a part of the GNSS. Man, I really wish I didn't have to change that. GNSS SDR. So all of that's a piece of it. Of these 25 pages, the one I found most interesting after crawling through the GPS spec for about 4 or 5 days, all right, was page 17 in subframe 4. This is a literal part of the GPS spec that allows GPS command to send special messages to any GPS receiver or every GPS receiver on the planet. And they're just basic ASCII. So modifying the GPSSDR Sim code, the spoofing code, to allow the addition of a page 17, I can now create my own special messages, which, because I control both sides of the conversation, I can then build a parser for page 17 within GNSS SDR to interpret those commands and run programs based on whatever command I happen to have. So once again, I can be sloppy here. I own both sides of the conversation. Once again, removing high-risk components, high-risk activities, things I can't test from my research pipeline at that point. So this is a fun one. I have no idea why it's only capital letters, but is what it is at that point. Okay, so here's the basic idea of the covert implant. So I build this in the actual GNSS SDR, the receiver side of this conversation. And I build it into, and I wish, does this have a laser pointer? Yes, it does. Okay, if you can see this, which you may not be, these here, I don't own these. These have to be different, basically on a per satellite basis. However, starting here at these 16 bits and continuing all the way through, I own this whole communication. I can say whatever I want within reason. All right, and that's about, I forget, I think it's like 16 bits, something like that, or 16 bytes. So I can put a pretty reasonable sized message together. No, excuse me, 22 bytes, something like that. Anyway, I forget. It's really bad at being up in front of folks. So the idea is I wanted to do some testing, so I wanted to send text to the console, a little bit of hello world here and there. At that point, what I have as well within the system, and this is currently still being worked on, is that I have what's known as the target list. And the target list is built from a scan. So I can instruct the GPS code to scan a network, is the idea, and anything that it finds valid as part of that scan, it holds in its target list. After that, I can then tell it, okay, go exploit those targets. So there's a Modbus protocol here I'm still working on that would then eventually go and exploit those pieces. So, and then at the last point, what I can do is I can clear the target list. So if I've decided, okay, I'm done with all my operations, or I want to do a new operation, you then send it the clear target list, pray that it got it, of course, and then you can redo scans again. So building this into the code is reasonably straightforward. They built a lot of library functions that allow me to extract data from frames pretty well. This is an excerpt of the code right here. So this is where, I was right, there are 22 bytes. This is saying within the code, okay, go from bit here to bit here, pull this out, and turn it into a character. All right, so these are just the constants that say, go from this bit to this bit within the frame message. So the problem here that I have is that, once again, I'm still building all of this on my own, and testing capability going from one program to another is still, it's not very good. I still have no idea what, if there's a problem, it could be within my file format too. So I've got some work to do on that side. But we've started the code on this side. GPSSDR Sim doesn't natively build page 17. It uses basically stubs. It's not very advanced from that point. Once again, all it does is take in the bare minimum necessary to spoof L1 GPS. So the code here, though, is whenever they're building anything for subframe 4, all right, set up an option within my own part that says, hey, if this option is enabled, add a page 17. And I didn't put the page 17 code in here, but it's where making edits is pretty straightforward on where you have to go. At this point as well, I have a command file. So this particular command file prints hello world to the console, or it's intended to print hello world to the console. It then scans the 192.168.1.1/24 subnet, and it goes there looking for port 502. You notice how I have to pad all of this stuff? It's because of the way that the frames work and because I'm lazy. So once again, best effort. Next thing it does is that it takes a Modbus-based payload, and it says, okay, go change a couple of registers within the Modbus. Again, TBD, but there's some Modbus code available for doing this kind of stuff. And then after that, does another scan. No, excuse me, it clears the target list, and then outputs mischief managed. And so that's the whole idea of that. Here is my first attempt, starting off to generate an actual, that takes in the command file and parses the command words into a page 17 and then outputs it to a file. So this isn't recognizable by GPSSDR. This is where I fell down right after Christmas. This is where my project stopped before I had to come to S4 and I had to give Dale the presentation. I'm continuing work on this. It's definitely a problem right now where I'm generating the wrong type of file. All right. I hope this brings you, gives you some ideas as far as GPS goes. I hope it helps drive through a point regarding hardware security. You know, don't get me wrong, this is pretty advanced. Like, if an adversary is doing something like this, they're probably doing other things as well. All right, but I want us to think about like the things that come into our environment, the things that we allow in, the data that's allowed to come in. All right, and take a good hard look at it and say, okay, is this really something that I want to have come in without any checks or balances? So we made that mistake in Marine, and now GPS spoofing is now in use, in active use in several countries around the world. It's been found in a couple of different places. Android phones themselves have protection against GPS spoofing, iPhones a little less so. And there's now an entire cottage industry now of what's called GPS firewalls. There are at least 2 products that I know of that actually will attempt to detect bad GPS signals, spoof GPS signals as they come down the wire and yell at you or block it as it comes in. So if there are any questions, I think I've got about 7.5 minutes left, and I'll be happy to take a few.
Thank you, Michael. That was good. The GPS that I run into is mainly for timekeeping. So when a radio receives a signal, it's to deliver time through NTP or PTP. Mm-hmm. So what is it about these applications that receive data and then do something? And how many radios do you know that are built that way in order to receive a command over GPS?
I am unaware of any that are currently built to accept a command over GPS. All right, this is something that I did. This is something that I'm investigating. The GPS clock that you saw me pull up, okay, come on, there we go. This one has what's called a GPS module inside. I have been unable to dump firmware from it, but the module itself only accepts valid GPS stuff. Once again, I control, for this proof of concept, I control the horizontal and the vertical. I control both the sender and the receiver. All right, so I've got a lot of play here. So as far as like a proof of concept or whether or not something like this exists in the real world, I haven't seen it, and there are things in place right now that would make it difficult to do. If anything, I think I've shown that. It's a high-risk activity to go and do this on your own. Did that help? Okay. Any other questions?
So 2 questions for you. In terms of, let's carry this forward to its logical conclusion, back to the high-risk implementation where you actually have put this in some sort of GPS receiver. You're out there sneaking outside the substation with your antenna and your hack RF to send your malicious command to the GPS receiver that you know exists inside the substation. Meanwhile, you have a whole constellation of satellites sending down their standard messages. When you send your GPS message from your hack RF with your extra payload on page 17, are you acting as if you're one of those particular satellites, or are you trying to act as if you're the entire constellation? Where are you fitting your CDMA transmission in with the rest of the constellation?
Pick. You can pick.
Okay.
All right. So you could be a GPS satellite from the other side of the world. It does take in these subframes. It processes the subframes.
Okay.
So in general, though, you would be sending it either as one satellite or as multiple satellites.
Okay. Second question for you. Are you aware of any modules out there that, in fact, expose that page 17 to the rest of the environment? I think about, embedding a module inside of a device. More than likely, I'm just getting the module off the shelf, so I'm going to have access to the page 17, and I'm going to have firmware elsewhere in the device that looks for that page 17.
Yeah. So the GPS module that I was looking at doesn't, as far as that goes. So the idea is that it will process out page 17 and push it out to whatever GPS clock. So for this one, NTP has extensions that accept what's known as NMEA directly out of a GPS module, and NMEA doesn't have those special messages in it, from what I've been able to tell. So this wouldn't actually work on a commercial GPS module. You'd have to mess with the GPS module itself to permit a lot of page 17. That being said, there are modules out there that have more advanced functionality, that can do a lot more, and that output a lot more. Make sense? Okay.
Yeah, hi. Oh, sorry.
Go ahead.
I was wondering, what is it that those two vendors that have the GPS firewalls, what are they protecting against?
Yeah, they're protecting against time and location spoofing. So the technical documentation that I've looked at there is that they are looking in differences in signal strength. So you have to overpower the GPS signal. Not that difficult. It's really not. GPS is, once again, one of the weakest signals out there. So it's looking for a ridiculously high signal strength. And it says, hey, this is possibly spoofing. The other one, too, is that it's using certain antenna configurations in order to determine directionality. So if it says, oh, hey, this appears to be coming from a terrestrial source, this is probably spoofing and not the satellites themselves coming through. As well as they're looking into the protocol itself. Like, for instance, like I said, bare bones L1 from that GPSSDR Sim, it's got a lot of blank spots in it. So if it notices, hey, there are a lot of blank spots here, this is probably spoofing, ignore it. So, does that help? Okay. Are there any other questions? Thank you so much for your time. I wish I had a POC for you. I really wanted to have a POC for you. Come to S4 next year, all right? And I'll at least have the other plan working, and we'll see how far I get on the other side of this. This was a really fun kind of thing. If you pick a project to stretch yourself on this, do yourself a favor and don't put in a conference presentation abstract, or else you might end up here going, this is what I was working on. It was a lot of fun. Here's my process. I hope you enjoyed it. No POC today. Have a nice day. So anyway, thank you so much for your time.